Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Daffa Dzakwan Balaw, NPM 22060615596. And today I'll be reviewing and also uh, correcting the answers that I've given in my final test. And in the test, we got five different problems for in mechanical fluids, and I'll be reviewing them and correcting them one by one. And of course, as with any other, we'll be using the DAI5 method to review and to solve these problems. And so we'll get on with our first problem. And of course, we'll have to set our intention first. Here I've wrote that my intention, I've set in my heart, mind, and on this paper that I intend to stay conscious, going back to the reason and my intention of rolling into the first destination. I attended the academy so that I can gain knowledge, make my parents proud, contribute to my nation, and also serve God. From that point up until now, my intentions are the same. Now, in the position I'm in, where I'm faced with this fluid mechanics problem, I also intend to solve this problem so that I can understand more from it and gain knowledge while still, of course, staying conscious of God, being grateful to Him. Now we can move on to our initial thinking. In this, I wrote that the problem itself states that an airflow of up to 1 meter cube per second at standard condition is expected in a 0.25 meter diameter duct. An orifice meter is used to measure the rate of flow. This is an orifice meter, and the manometer available to make the measurement maximum rate 300 millimeters of water. Determine the diameter of orifice plate that should be used with D and D per 2 pressure taps. Determine the head loss if the flow are at the vena contract is 0.65 the orifice diameter. So here I've visualized the orifice and the duct itself, the airflow, 1 meter cube squared. There's the orifice, we're going to measure the rate of flow. And in here I have two idealizations, the one that I wrote in the paper and the one that I shall be correcting and I shall be adding. So idealization, I wrote in the three basic principles in fluid mechanics are conservation of mass, conservation of momentum, and also conservation of energy. So considering that the mass, momentum, and energy are solid states the same and conserve basic principle applies, so we can assume flow is steady and the air is incompressible. And here I simplified using Bernoulli equation. But here I corrected in my idealization that we should assume the rho of the air is 1.23 kilograms per meter cube, and the mu is 1.46 10 to the power of minus 5 PA. So we use a standard fluid dynamics equation to relate flow rate, pressure drop, and the orifice diameter. And here is the formula for mass flow rate, and then we'll also use the formula for pressure change and the height of column in nanometer, and also the Reynolds number formula. And also here's the formula for head loss, where we can assume no neglect delta z and alpha 1 delta 1 squared is equals to a alpha 3 delta 3 squared. So hence the h on r is this, and then these are all the assumptions and the simplifications that we'll make. So then we'll move on to the Reynolds to the instruction set. We'll use the Reynolds number to find that the outcome is 3.50 times 10 to the power 5, and the flow speed at 2. We can apply to pressure change 3 and 2, and we'll get that P3 minus P2 is 1290 newtons per meter squared. And if we apply that to head loss, we'll find that the H on air is 1250 newtons times meter per kilograms. Now that we got all that, we can apply that to the head loss through the orifice. Hence, we'll get that the head loss to the orifice 0.44. On to the second problem. So, of course, set tension again. The tension is still the same. It's still the same throughout. Solve this fluid mechanics problem. Also gain and serve. Be grateful to God Almighty. And the initial thinking is that the problem states that spray heads in agriculture spraying systems are to be supplied with water through 500 feet of drawn aluminum tubing from an engine-driven pump in its most efficient operating range. The pump output is 1,500 GPM at a discharge pressure not exceeding 65 psig for satisfactory operation. The sprinklers must operate at 30 psig uh, or higher pressure. Minor loss and elevation changes may be neglected. Determine the smallest standard pipe size that can be used. So here we know that 500 drawn aluminum tubing. I visualize that. It's kind of a bit hard to see, but it's in its most efficient range. The pump is 1,500 GPM at a discharge pressure of not exceeding 65 psi, and satisfactory operation of it must operate at 30 psi or higher. So here in my initial thinking, we can apply the energy equation, which is this, and we'll also use the Reynolds number and idealize it even more from there. And from the energy equation, we can further idealize the H1, and then we can get V from the Reynolds number, which is just from there. And then we'll get the delta P. So in my correction for this specific problem is that, well, first we'll have to find the delta P, which is P1 max and P2 minimum, and that is 65 minus 30 psi, which is 35 psi, and the head loss we can get with uh, this formula, and then we'll get the head loss simplified is FL per D, where delta is 2 squared per 2. And then we'll assume here, this is the part of idealization, we'll assume that it's a steady flow. The flow is incompressible. The H1, the all air is HL, and i.e. HLM is equal to 0. And then Z1 is equal to Z2. Then delta 1, delta 2 is the same, equal to delta. And then we'll go to the pressure change. This is the formula for the pressure change. And then we'll use the Reynolds numbers in terms of Q. So the Reynolds numbers will be 4Q P pi LD. And then the flow rate, then we'll get to the instruction set. We'll get that the flow rate for Q is 1,500 times uh, min per 60 seconds. It's 1 second. It's divided by 60. And it's also divided by 7.48 gallons. And we'll get that to 3.34 feet cube per second. And I will input D in 6 inches and 5 inches to the Reynolds number, and then also to the delta pressure, and then we'll get that the delta pressure is 56.4 pound-force per inch squared, so that the minimum diameter for pressure drop is 6 inches. And we'll move on to the third problem, and always, of course, for all of these problems, I set my intentions for the same, which is to solve the problem, gain knowledge from it, and while also being conscious, keep staying conscious, and understand, God from it, and be grateful towards Him. And for moving to the initial thinking for problem number 3 is that the problem states that a dragster weighing 1,600 pound force attains a speed of 270 miles per hour in the quarter mile immediately after passing through the timing lights. The driver opens the drag parachute of area 25 feet squared The air and rolling resistance of the car may be neglected. Find the time required for the machine to decelerate to 100 miles per hour in standard air. Now, here I visualize the dragster. Poor visualization, I know, but this is the best I can do. And it's going at 270 miles per hour. Weight is 1,600 pound force. And after passing the timing lights, it opened parachute area of 25 feet squared. So here's the parachute, and the area is 25 feet squared. Now this I wrote, we can use the formula of Newton's second law for the drag, and use the formula Fp equals half cv. And for realization, I idealized this more. I didn't get into detail because I was sort of confused while writing this, and I didn't know where to go from here. So I idealized it more, and uh, I choose it so it equals to the derivative of mass, a derivative of velocity. Sorry. So in my correction, the idealization should be, since CD equals FD per half rho v squared a, then FD equals half CD rho v squared a. And we'll substitute that into Newton's second law, and we'll get this. And then separate the variables and integrate. So then we'll get the time as this. And now to find the time itself, we can move on to the instructions and input all of the numbers and data that we have, and we'll get that the time is 5.05 seconds, and we can verify that using Reynolds number. We'll just input all of that into the Reynolds formula, and then we'll get that the Reynolds number is 5.27 times 10 to the power of 6, which means that it is in fact valid. Move on to the fourth problem, and I'd argue this fourth problem is not even a problem itself. It's more of a situation, or a sort of scenario that we are being depicted, and we're supposed to show what can we analyze from it, and what can we get from it. So my intentions were still the same. God, grateful to him, gain from this problem says scenario. And then the initial thinking, the problem itself, it shows this visualization, which is a wave, a fluid moving at speed delta v, and then here the fluid is moving, and at here the fluid is at rest, and here's the y, and this is the delta y. So if you'd imagine, like, you're at a beach. Let's say you're at a beach. I'm sorry. So let's say you're at a beach. Here you are, and then there's a big wave coming. Now there's a wave coming right here. Now this would be the y, and this would be the delta y. Delta y. And it's basically the same thing. So fluid is moving. The fluid is moving at speed delta v, and right here the fluid is at rest. The fluid is at rest. So you can think about it like that. That's basically what this depiction is trying to tell us. And with we can change this depiction and put it at another, it's relative to the absolute coordinates, and we'll get that, well, fluid is moving at speed c minus delta v, so speed c is constant, and then this here is the wave at rest, and then this is the control volume, the fluid and moving at speed c, so it's almost the opposite kind of, but it's just another perspective from an absolute coordinate. So Here we can see two coordinates, which are the coordinates that are absolute and the coordinates relative to weight. If at rest, we can get that the delta v is stable and that speed wave is moving. The speed wave moving is stable. The control volume we can get is this, and then haven't really finished this fourth problem because I was quite confused as what to do. But now that I can actually correct it and move on to the idealization and instruction set, there I can tell you that the idealization, we should assume that the flow is steady. It's an incompressible flow. There's uniform velocity. There's frictionless flow, hydrostatic pressure distribution at each section. And then we can move on to the instruction set, which is we can get a lot from this, and especially we can get the continuity equation itself, and then we can apply that to the control volume to find the change in speed, and then we can find the total height of the wave. We can get all of that data that was previously unknown here, and we can all get that data for this formula. So if this problem would have a uh, specific value to any of the data that's provided, we can find all of that using this formula. We'll move on to our last problem of the final test, and as of course, as always, my intentions are still the same until the end, which is the gain. It's the gain from solving this problem while staying conscious of God and understand and get closer to Him from it. So the problem here states that air flows isentropically through a converging nozzle at a section where the nozzle area of 0.013 feet square, the local pressure, temperature, and Mach number are 60 psa, 60 psi, 40 Fahrenheit, and 0.52 respectively. The back pressure is 30 psi, and the Mach number at the throat, the mass flow rate in the throat area are to be determined. So given that the airflow through a converging nozzle at the condition shown, this the visualization. So the M1 is 0.52, T1, P1, and A1 are all shown here. And I'll move on to the idealization. We can see at T, see her T here. This is the zoomed in version, I guess you can say. The PB is 30 psia. The A1, P1, T1, A1, we can get all that from there, from the T1 here. And we can determine whether flow is choked or not by checking the pressure ratio at the exit, and we can use the ideal gas also. So here in my correction, for the idealization, we'll assume that we have ideal gas behavior for the air and convert the temp to Rankine. And as for the instruction set, we can check the stagnant condition of this formula, and the stagnant is 72 psia, 72.0 psi, and the back pressure ratio, we'll get that 0.417 is lesser than 0.528. For the Mach number is 1, and for the flow speed at 1, we can get that with this formula, and we get the V1 is 570 feet per squared, and the density at 1 we'll get with this formula, we'll get that it's 0.324 lbm per feet cube, and the mass flow rate is of course with m equals rho va, we'll get that at 2.40 lbm per second. And for the isentropic process, and since we changed that to Rankine, we'll get that with this formula, and we'll get that it's 1.303, and from all that we'll get that the throat area, which is AT, is 9.98 times 10 to the power of minus 3 feet squared. So that is the end of it. Hopefully that with this video and with this correction for my final test, um, able to correct my final test answers correctly, and that it'll be useful, and I will gain more from it, and everyone watching here will also gain more from it. I hope that my explanations were clear and that you were able to understand. If not, you can put a comment down in the comment section below and give any of your opinions, or leave a like if you think that it was good. And before that, thank you for watching, and assalamualaikum warahmatullahi wabarakatuh.